to Science Fantastic with Professor Michio Kaku. Every week on Science Fantastic, we explore the cutting edge of science, and we profile some of the most amazing developments in science and technology. And today, we're very glad to have with us an astrophysicist all the way from the Netherlands, Professor Heino Falke. He is the author of an exciting new book called Light in the Darkness, Black Holes, the Universe, and Us. It was a few years ago that for the first time in history, a photographic image of a black hole was revealed to the people of the world. It made headlines around the entire planet, and so we'll talk to one of the people involved with that historic photograph, the first ever image of a black hole in the galaxy M87. Well, let's now talk about black holes. There's a new book, Light in the Darkness, Black Holes, the Universe, and Us, which talks about the fact that history was made a few years ago when scientists were able to actually take a photographic image of a black hole in another galaxy. The book is by Professor Heino Falke, and he's a professor of astrophysics at the University of Radboud in the Netherlands. And we're very honored to have him all the way from Europe on Science Fantastic. So, Professor Falke, glad you could be on Science Fantastic.
Yeah, I'm glad I can be with you today.
Okay, well, the first question we always ask our guests is, when you were a youth, think back now when you were a kid, what steered you in the direction of science and then in the direction of astronomy? What was it? Was it a book, a trip, something your parents said? What steered you in that direction?
Well, the first thing I can really remember was actually the moon landing. It was Apollo 15, actually. I was a little kid, 4.5 years old, and I saw... In fact, I was the only one in the room watching it because it was already old news. The adults had already seen the previous moon landings, and they were tired of it. But I was glued to the television and watched it for hours while the other kids were playing outside on the street. And I was following it, and seeing these people running around on the moon. I was thinking, wow, you can run around on the moon. And, I already intuitively understood that this was a big, amazing thing that happened. By the way, they landed the Falcon on the moon, which fitted my name. So that's Falcon means falcon in English. So that was quite funny. That was an inspiring moment. And I think my grandmother was the other inspiring person because she's from really East Germany, which is now Russia. And she grew up in a very rural area, and she wanted to become an astronomer, seeing all the stars up there. And she wasn't allowed to because she was a woman. She was allowed to study English, nonetheless, not natural sciences. Nowadays, of course, we're blessed to have so many women in science. But at the time, that was a dream that wasn't, allowed to come true for her. So I think she instilled a little bit of that passion in me as well.
Okay, and then what steered you in the direction of astronomy and specifically research in black holes?
Well, I was always a curious kid. I'm this nuisance, kid, and ask always why, and you get, further, and why is that, and what's behind that, and, what's behind the heaven, and what's behind heaven, and what's there, and so forth. So I was, going all the way through the fundamental questions that I was interested in. And so I really want to go, I really have in my studies, I want to go to the ends of space and time, literally. So where really the fundamental new questions are. And when I was doing my studies, black holes were clearly, at the center of what would be new. Because one of the, you were talking about the unification of the big theories, right? And one of the outstanding questions still is, how do you get gravity and quantum physics together? How do they rhyme? And at the edge of black holes, they fail, right? It's a big question. How do you describe black holes with a quantum theory and general relativity of Albert Einstein? That was already, known in the, through the work of Hawking and others in the 90s. And astrophysics was starting to discover black holes in the nuclei of galaxies.
Welcome back to Science Fantastic with Professor Michio Kaku. With us today, all the way from the Netherlands, is Professor Heino Falke. He's a professor of astrophysics in the Netherlands at the University Radboud, and his new book is called Light in the Darkness, Black Holes, the Universe, and Us. Well, let's wind the videotape backwards now and go back into the past. We're now in the 1700s, and there's a clergyman by the name of John Michell. He was familiar with Newton's laws of gravity, and he made a prediction that there should be a new kind of star out there called the dark star. So, Professor Falke, can you tell us about John Michell and the fact that by using Newton's laws of gravity hundreds of years ago, he predicted the existence of what we now call black holes?
Yeah, that was an amazing thought. It was actually a little thing. It was not a big theory that he developed, but he was just saying, look, if there's a star which has such a strong gravity that it can actually attract light, and where the gravity is stronger than light, it could escape from, you would have a dark star. And the only way you could see it is from the planets going around. You would not see any light and emission coming from it, but you would see planets maybe orbiting around it. And you could only see it through the force of gravity. And that was actually a very radical and innovative thought. And already the idea that light could be bent by gravity was very amazing, and had to do with the nature of light. Is light a particle or is light a wave? And it really took until Einstein that this question was resolved. And it was shown that light can be particle and wave at the same time. It's both. And that gravity can actually deflect light by deforming space-time, so light actually is deflected. And then it was actually Einstein who didn't really believe in black holes. It was, a mathematician, Schwarzschild, and physicist, who, first calculated the equations that describe a black hole. And then you could actually see that light is actually going in circles around that object. If you have a lot of gravity, a lot of mass compacted into one little point, and then, light could go in a circle, and you would have a region which later became known, many decades later only became known as the event horizon, where light would actually not be able to escape anymore. It would be completely dark. Light would be trapped, as would be any other information. And Einstein thought these kind of objects cannot exist. They cannot.
Okay, so Einstein, as I understand, writes a paper trying to disprove the formation of a black hole, showing that the swirling gas will never condense into a black hole. But then comes J. Robert Oppenheimer, the man who would later build the atomic bomb, and he comes up with a new mechanism to create a black hole, not swirling gas, which will not condense into a black hole, but an implosion method. So explain to us what Professor Oppenheimer proposed, which we think is the way to create a black hole.
Yeah, now what we know today, how black holes are created in the first place, and that's pretty much the seed that Oppenheimer laid, is that you have a star which comes to the end of its lifetime, and it starts to collapse. And then gravity takes over. The matter will be compressed more and more. And if you have a lot of matter compressed into a small area, the gravitational attraction of it will become stronger and stronger. And so, you have to have more and more force and more energy to keep the star stable. At some point, gravity wins, and there's no force in nature that can stabilize this collapse. And so gravity will become just stronger. It's a runaway process. It will, collapse into a point, essentially. It looks like this should collapse into a point forever from the outside. A never-ending collapse into an ever smaller space that becomes a small point. And, we see these things happening, big explosions, supernova explosions. And Oppenheimer wasn't far away from big explosions, we know.
Yeah, in fact, it's said by historians that this implosion method of creating a black hole, he actually used to create the Nagasaki bomb. The Nagasaki bomb was also based on imploding plutonium rather than imploding hydrogen in the star. But the idea of implosion came from a black hole and was later used to build the atomic bomb. But anyway, let's move on now, because people realize mathematically that if you fall into a black hole, all sorts of distortions take place. In fact, Arthur Eddington, famous astronomer who verified Einstein's theory, said that this is so crazy that there should be a law preventing stars from behaving this way. So what happens if you fall into a black hole?
Actually, if you fall into a black hole, nothing special seems to happen. You approach the black hole and you see this big darkness in front of you. And once you go through the event horizon, you see actually the entire universe, the light of the universe condensed into one little flash of light. And then you go into this black hole, you're still alive. In fact, if you have a very big supermassive black hole, then you can actually survive falling into a black hole, at least for a little while. And you keep falling. But the point is, actually then space itself will actually drag you towards the singularity. You're traveling, so to speak. You could stand still in time, but space will drag you towards a central singularity and will crush you to death in the end. If the black hole is rotating, which is also possible, you not crush into a point, but all the matter is sort of collected into a ring. And then the inside of a black hole becomes completely crazy. You could actually travel in time. You could start now and come back, now again, by, rotating around that ring-like singularity. So really cause and effect seems to change. From the outside, you will not see anything what's happening there. You would only see you falling towards the event horizon, and you would see time slow down, getting slower and slower every time. And if you manage to escape from a black hole before you go in, you'll be at a very different age from where you started. You'll still be young, while your sibling, for example, has become an old man or an old woman. Because time is slowed down near black holes. So really the laws of physics, they're okay until the event horizon, and afterwards they become a bit crazy, so to speak. And black holes really, challenge our intuition of how physics works and how space and time are actually behaving.
Okay, so let's summarize this, because Hollywood, of course, has had numerous depictions of this process. So you're saying that as you fall into the black hole, if you're in the frame of the rocket ship, you feel basically not too much. Distortions are minimal, but from the outside, all sorts of distortions take place. Time slows down, things like that happen. But also there's a process called spaghettification. So explain to us what happens when your body turns into spaghetti.
Well, I haven't experienced that yet, so I can't give you all the details, unfortunately, or fortunately, perhaps. If you're falling into a small black hole, and a small black hole, I mean something that's, tens of miles in radius, that's created by the explosion of a star. Then you are rotating around this black hole in milliseconds. You within a second, you can rotate a few thousand times around that black hole. It's a whirlwind of rotation. And then your feet are attracted a bit more strongly than your head, because you're closer to the black hole than your head. And so it's dragged further and faster around the black hole. You wind up, you become a long spaghetti wound up around this black hole. I suspect this will be a very unpleasant experience, I must say. That's why, if you ever decide to jump into a black hole, pick a really big one. Pick the one that we looked up, that we made the image of, M87. It's 6 billion stars, black holes that combined into one supermassive black hole. And then, it's so big, it's the size of our solar system, in fact, a bit larger than our solar system even. Then the difference between your feet and your head are really minimal.
Welcome back to Science Fantastic with Professor Michio Kaku. Welcome back back to Science Fantastic with Professor Michio Kaku. With us all the way from the Netherlands is Professor Heino Falke, author of the book Light in the Darkness, Black Holes, the Universe, and Us. And we're talking about, well, the black hole in our own backyard, the Milky Way galaxy. Dead center of the galactic nuclei of the Milky Way galaxy, there is a monster black hole, maybe 2 to 4 million times the mass of our sun. And, well, one day we're going to get close-up shots of that black hole, too. So tell us a little bit about, now, the black hole in our own backyard.
Yeah, it was found in 1974. They found a radio source, some radio-emitting, very small object, and it looked to be very much in the center. And then, when I started my PhD, people used infrared cameras, near-infrared cameras that came from, actually, night vision cameras. And they would be able to look through the dust of our galaxy, which was obscuring our view, and they saw stars. And they saw stars moving in the center of our Milky Way, actually not moving every hour, but moving from one year to the next. And you would see stars going around in a perfect ellipse on a 16-year time scale. Like a planet goes around the sun, that star would go around with 10,000 kilometers per second, or about 10,000 miles per second, around that particular radio source. If you take, Kepler's laws of, the planet's motion around the sun, you can determine what mass you need in order to keep stars tight in the center of the galaxy. They move so fast. And you need 4 million times the mass of the sun concentrated in that radio source into a very small region. And I was, looking at this and trying to explain the radio emission of this, and I realized that a certain type of radio emission, a certain frequency, a certain color of the radio emission would come from almost near the event horizon. And that was exciting, because I was thinking, how would a black hole look like if you illuminate it with light from all directions? Well, you see a darkness. You see the darkness of the shadow. You see a shadow of the black hole. And that shadow, something it took me a little while to realize, is actually a little bit larger than the black hole itself, because the black hole acts as a lens. It magnifies itself. You see a reasonably large shadow. And, that shadow would be the size of a mustard seed in New York as seen from Europe. You need a telescope with which you'll be able to read the New York Times from Europe, right? The New York Times that you have in New York. Such a big telescope you would need to have, but then if you have this, you would be able to see that darkness, that shadow. And that was a prediction we made, and we also knew at the time how to build such a telescope. You need just a telescope the size of the world. Well, you can do this by combining telescopes, by combining them virtually into a network that creates a virtual telescope in the computer that acts as if the entire world were a big radio telescope. And that gives you the resolution to peer into the heart of our Milky Way and potentially resolve that shadow. And that was the idea. And that was such an amazing moment, when I realized, wow, that's possible. We may be able to see a black hole. That was 25 years ago. And it took almost 25 years to realize this. And 2 years ago, we succeeded, not with this source yet, but with another black hole in another galaxy, but equally beautiful.
Now, your group made world history by showing us the image of M87's black hole, a nearby galaxy. When will your group also release the first photograph of our own homegrown black hole in the Milky Way galaxy? Is that coming pretty soon?
That's our big dream, of course. I'm not allowed to tell you when and what we will show. That's still a secret. But I can tell you we are working on it, and we'll try to get it to you as soon as possible, and hope that this year we can be able to publish some results from this. Welcome back to Science Fantastic with Professor Michio Kaku.
Once again, our special guest today is Professor Heino Falke. The book is called Light in the Darkness, Black Holes, the Universe, and Us. And we were very fortunate to get him all the way from the Netherlands, where he is a professor of astrophysics. Well, when we last left off, we were talking about black holes and how to detect them. Traditionally, it was thought that we would never be able to detect the event horizon of a black hole because they're so far away. But a radio telescope is simply not powerful enough to resolve a black hole. So what this group does was they lashed together several black holes to create an effective, gigantic radio telescope the size of the planet Earth. And according to the media reports, this effective radio telescope is so sensitive that it can discern an orange on the moon from the planet Earth. Is that right? Is that how sensitive this effective radio telescope was?
Oh, absolutely. And in fact, it would even be a tennis ball, which I think is a little bit smaller than an orange. Or as I said, a mustard seed in New York is seen from Europe. Yeah, and that's what you can do by using the perspective from all parts of the world and combining them, because you're looking on a slightly different angles. And what we do is we actually record the radio waves that come from outer space, record them on actually hard drives, we store the waves, and then we can process and do what a telescope would do. A big reflector dish, would reflect the light and would focus it and bring and combine the light in the focus. We do that in the computer. And that, gives you something that is, a telescope the size of the Earth.
Okay, now let me ask you a question that comes out of science fiction, but also mathematics. Mathematician Roy Kerr found a solution of Einstein's equation back in the 60s with a rotating black hole, as you mentioned. It collapses to a ring, not a dot. But if you fall through the ring, you wind up in a parallel universe. You go through what is called the Einstein-Rosen Bridge. Now, this is, of course, pure mathematics. We live in a physical universe. We want to know what really happens. But what are your thoughts? What's the latest developments in terms of what happens if you fall through a black hole's event horizon, through this ring at the very center? Do you wind up in a parallel universe, never to come back? Or are you simply crushed to death? Or what do you think happens?
Well, I think we can agree on you never come back. That part I think we can agree on. The calculations really in the inside, the innermost inside of black holes, are going to be very difficult. Right now, people don't think that a Kerr black hole, the one you described, actually are gates to a different universe. They are not traversable. In order to create a traversable wormhole, you actually need to invent a certain type of matter, not antimatter that we know, but matter with negative energy. And you'd have to keep that stable. So there's currently no theoretical underpinning or idea how you could really make a traversable wormhole that would allow you to travel. Nonetheless, we looked for, whether the data that we have would be consistent with a wormhole, right? Maybe, we are stupid. We're not smart enough. And so there are predictions how a wormhole, a traversable wormhole would look like. And it would have a different size given the mass and the curvature of that space-time that we see. And it didn't match. So we are reasonably confident that what we see is an ordinary black hole, not a wormhole. We don't know whether it's rotating, though. And that's one of the next big questions. Can we find out how fast the black hole is rotating? Does it have a ring singularity? We would not be able to see the ring singularity in the very center, but we would see the effect of rotating space. Space would co-rotate with a black hole and would drag matter with it. It would drag magnetic fields with it. And there are some indications that, these powerful plasma jets that we see in the center of M87, there's the plasma shooting out, that this comes from, partially at least, from the effect where magnetic fields are dragged along by the force of gravity, by empty space, essentially, co-rotating with a black hole, and then shooting plasma out along the rotation axis with almost the speed of light. And we are not 100% certain yet that we can see that we can prove this, but it looks very promising. So that's one of the research topics of the coming years, actually. We need much better data to be really sure about this.
Okay, well, we are talking about science fiction, so let's talk about white holes. Some people claim that if you fall into a black hole, perhaps you're spewed out the other end as a white hole where the direction of time is reversed. So instead of falling in, you fall out. And that is a solution of Einstein's equations, but is it a realistic solution of Einstein's equations? What are your thoughts?
Yeah, it's a very good question, and we've been surprised quite often that something that looked very strange mathematically also existed then in the real nature, like the positron, antimatter, right? So you invent something like complex numbers, what's the square root of -1, and here comes the positron, and you find it in real nature. And so, do white holes exist in the universe? And it's up to physicists and astrophysicists to tell. Mathematically, it's possible, but is it part of the real universe? That's a big question. And so far, we have not found any evidence that white holes exist, that they are out there in the universe. And so we will keep looking, but I'm not very optimistic. Maybe that's one of the mathematical unicorns that look nice on paper, but may not be existing in the real universe. But who knows?
Well, unfortunately, we have run out of time. Once again, our special guest has been Professor Heino Falke. The book is called Light in the Darkness, Black Holes, the Universe, and Us. So, Professor Falke, thank you so much for being on Science Fantastic.
Well, thank you for having me. I had a wonderful time here.
Okay, and once again, the book is called Light in the Darkness, Black Holes, the Universe, and Us. And this is Professor Michio Kaku. Bye now.